All right, so let's start then. Before the break, we were looking at MOSFET models, and we were done with the basic operation of MOSFET, the large signal DC and small signal model. So today, let's start with MOS amplifiers. Okay, so let me remind you of the MOS model that we had done. We had said that the MOS can operate in linear and saturation regions. In the linear region, the MOS is governed by this particular equation. Of course, remember that linear is only for very small drain to source voltage here, when you can ignore the quadratic term, and then the relationship is linear. But in general, we call this, the region of mode of operation as linear or triode mode of operation here. So this is the governing equation. There is a parameter here, beta n, which depends on Kp and W by L. And as I said, that once you choose a technology, Kpn is fixed here. And normally we choose L to be the minimum possible that is allowed by the technology. Normally, as I said, but many times there are advantages of choosing larger L as well. Anyway, so that's the equation for linear region. And this is the equation that we have for saturation region here. And this equation will hold when drain to source voltage is larger than saturation voltage, which is VGS minus VTHN here. And this is the expression for threshold voltage. The parameters in red are all fixed once you choose a technology. And depending on source to body voltage here, you'll have a particular kind of threshold voltage here. And as I said, for all our discussion, we'll use these particular values here. That the zero bias, zero meaning for zero source to body voltage, we'll use threshold voltage as 1 volt. Gamma, the body parameter here is 0.7. 2πf is 0.7 here. Kpn is 100 microampere per volt square. As I said, L will be 1 micron nominally. Lambda is 0.01. So these are the parameters that we'll use. And this was the small signal model that we had looked at. The small signal model under low frequency has these three elements: GM, voltage dependent current source GM VGS, GM VBS here, and R0. And this is how we calculate GM. Once we know the bias point, DC bias point, then one can calculate GM using this expression. One can calculate R0 using here, and one can calculate GMB here. So all these three terms here, GM, GMB, R0, we can calculate using the equations that are given over here. And when it is high frequency operation, we add the capacitances. We have CGS, CGD here. Two important capacitances, source to body here and drain to body here. Gate to body, we said in saturation is much smaller, and we'll neglect it. So these are the capacitances, and I had given you expressions on how to calculate each one of these capacitances. All right, so with that background in mind, let's start with the simplest MOS amplifier, which is a common source amplifier with resistive load. Now, all this, the treatment here is very similar to common emitter, common base, and common collector. We'll be doing similar things with MOS amplifiers, so I'm going to go over it very quickly. Okay. So we'll take a concrete case here. We'll take this is my N-channel MOSFET. We've chosen a size of 2 by 1. 2 by 1 meaning the width of the MOSFET is 2 micron. The length is 1 micron here. The supply voltage typically for us will be 3.3 volts for 1 micron technology. So 3.3 here. And 1.5 volt VG is used to bias this particular transistor. And we have a resistor in the drain. So note that is very similar to a common emitter amplifier, except that instead of a bipolar, we have a MOSFET here. So the first thing with any amplifier that we need to do is do the bias point calculation here. So for bias point calculation, note that the source, AC source, will be a short. And so we have 1.5 volt applied between gate and source. So what we'll do is DC analysis. We'll assume that the transistor is working in saturation region. Okay. So after assuming it to be in saturation region, this is the expression for current in saturation region here. For DC analysis, remember there was an expression, there was a term here, 1 plus lambda also. But for DC analysis, we'll ignore that particular term, because that 1 plus lambda is a small quantity. We'll not bother about it. Okay. So we'll use this simplified expression here. Beta n by 2 VGS minus VT n square. Note that VGS we know is 1.5, and beta also we know. Beta is Kp, W by L. W by L is given to you. Kp is also known. So everything is known here. So you calculate drain to source current, which is 25 microamps. All right. Also note that for these typical sizes 2 by 1 for a MOSFET, the currents would in general be in microamperes. In bipolar, you're familiar with currents being in milliamperes. Okay, so here you'll find currents in more in microamperes. So drain to source current then we can determine easily, assuming it to be in saturation region. Next is we determine what is the drain to source voltage here, VDSQ, the quiescent point here, and that's equal to VDD, supply voltage, minus the drop in this particular resistor, IDSQRD, and so we find drain to source voltage as 1.3 volt. Now, of course, at this point, what you need to do is verify that the transistor is indeed in saturation region. So what you do is you calculate what is the saturation voltage. And saturation voltage, you know, is VGS minus VT. So VGS is 1.5 and VT is 1 volt for us. So saturation voltage is 0.5 and 1.3 of course is larger than the saturation voltage. So transistor is in saturation and therefore our DC analysis is complete. We know the bias current and we know the voltage across this particular transistor here, and we have verified that the transistor is in saturation region. So it's straightforward. The next thing we do is small signal. So back to this amplifier here, and all of you know that in small signal what will happen is the DC sources will short out and we have to replace the transistor by a small signal model here. And this is the model that we'll replace. So wherever the transistor is, we'll substitute the small signal model here. And so let's do that then. But before we can do it, we need to know GM, GMB, and R0. And since we already have the DC bias point, IDSQ, VGSQ, and all that, so we can quickly estimate what the values of GMR, R0R, and GMB are. So all these values, using the expressions that we have already derived, we can estimate the values of these parameters here, GM, GMB, R0. Okay. So we know the small signal model then. We know all these terms here. So let's develop the voltage gain here. Develop an expression for voltage gain. So as usual, I'm gradually doing it. So this one is going to short out. We'll replace the transistor by its small signal model here. Now go back and see in this particular model here that because these, as I said, the body is connected to the most negative point in the circuit. And the most negative point in the circuit here is the ground here. So body is connected to ground and the source is also connected to ground. So this VBS will not be there, which means that the body to source voltage is 0, is a constant, and therefore the small signal body to source voltage is 0 here. So this current source will not be there. Okay. That's why when I'm drawing this expression, GMB is not there. GM, VGS, R0 is there. So we have substituted the model. We add RD. We add RD here. And of course, this one will be ground here. So that's the small signal equivalent circuit of my amplifier here. And it's straightforward to calculate. So we know that VGS will be equal to Vin, the applied voltage here. So this current source is nothing but GM times Vin. And this current source flows through a parallel combination of R0 and RD. And so we can very easily write V0 equal to minus GM Vin. That's the current source multiplied by RD parallel R0. And that's the net resistance at the output node here. And therefore, the voltage gain V0 by Vin will be equal to GM RD parallel R0. And in most of these amplifier circuits with the resistive biasing here, RD typically will be much smaller than R0. And therefore, we'll ignore the effect of R0 here. And AV then is simply equal to GM RD. GM times the net resistance in the drain node. And note that if I put in the values of GM that I had calculated and RD that you see here, 80K, we get a value which is equal to minus 8. The gain is pretty small. Unlike bipolar transistors, the gain in MOSFETs is usually smaller here. And the reason for this is that the GM is smaller. The transconductances in MOSFETs are smaller here. Okay, so we know how to calculate the voltage gain then, which is simply equal to GM times RD. All right. The next thing is output resistance. And recall that output resistance is determined by removing the input source here, shorting it, applying a source at the output here, Vx, finding out what is the current flowing here, Ix, and Vx by Ix gives you the output resistance. And so the moment you remove the source here, VGS becomes 0. The current source then becomes a open circuit here. Current source becomes 0. And you can see here Vx by Ix will be simply equal to, you can simplify, simply equal to RD parallel R0. And again, RD is much smaller than R0. So output resistance is simply RD. Okay. So that's also straightforward. Swing is also very similar to what we had done for a common emitter amplifier. So let's look at the swing part here. I'm sure you would recall this particular diagram here. We had drawn this particular diagram for a common emitter, common base, and other amplifiers also. So the idea is that we focus on this particular node, output node, because that's where the swing of our interest is. And we note that this particular voltage, there are two limits to this particular voltage here. It obviously cannot go above VDD. So that's one limit that we draw here. And the other limit, of course, is ground, which is the other limit here. So these two lines we can draw, VDD and ground. The other thing is, this particular node has a DC value, which is this particular line here, solid line, VDSQ. And note that when we apply a sinusoidal voltage, there is going to be a sinusoidal voltage at the drain at the output node also. So that's the sinusoidal part here. So the net voltage at this particular point is going up here and going down here. And what we have to do is ensure that my transistor remains in saturation region. If the transistor goes into triode region, then you start getting clipping and you start getting distortion. Now, how do I prevent my transistor from entering into triode region? Well, we have to ensure that it doesn't enter into this particular band here. And note that what is happening is, as the net drain to source voltage decreases here, note that the net drain to source voltage is decreasing. And what you have to do is ensure that the net drain to source voltage is always larger than VSAT. Okay, and that is what is VSAT or VDSAT is shown over here. All right, so you have to ensure that this minimum point doesn't go into this particular forbidden region here. At the most, what you can have is it touch this particular point. And from this extreme, it's obvious that this particular point here, the maximum cannot go beyond VDD here. So then we obtain two limits on output swing. One limit is that the limit that is coming from the positive cycle here, which says that the swing is limited to VDD minus VDSQ here. This difference here, VDD minus VDSQ, that's one limit on the output voltage swing. The other limit on the output voltage swing is VDSQ, which is here, minus VDSAT here. VDSQ minus VDSAT, so that's the other limit here. The actual swing will be determined by the minimum of the two. Whichever is minimum will decide on what the maximum swing is. Now, there is one limitation to this analysis, and that is, we have done this for common emitter as well. We know that if we use this particular expression, the prediction from this will not match with the experiments or with simulation. And what is missing here is the distortion. There's no discussion of distortion, except for the fact that we are saying that if it gets very close to, if it enters into this particular region, you'll start getting clipping and distortion. But otherwise, also we know that Mosfet is a nonlinear device. Even though you apply a perfect sinusoid here, the sinusoid that you get here at the output is a distorted sinusoid. Okay, and so we have to address the issue of distortion here, and we'll do it in a manner which is similar to bipolar. So the idea is as follows. This is the governing important expression here, which relates drain to source current to gate to source voltage here. So what we have shown here is that the net drain to source current has a DC plus a sinusoidal component or a signal component here, and the gate to source voltage has a bias component and a signal component here, VGS minus VT square. So that's the accurate relationship. Then from here we can obtain the relationship which is shown here, which is the small signal drain to source current, which is equal to GM-VGS plus GM-VGS square. So it's a simple rearrangement of this expression which gives us this one. Now in small signal model, what we have done, let me remind you, a small signal model is a linear model. And what we do is we ignore this nonlinear term. And therefore we end up with IDS equal to GM-VGS. But we know that in reality, the second term is also there, and that contributes to harmonic distortion. All right, so we want to determine what is the harmonic distortion, And note the source of harmonic distortion. The source of harmonic distortion is that the drain current and gate to source voltage relationship is nonlinear. In this case, quadratic. Similarly, in bipolar, the relationship between collector current and base emitter voltage was nonlinear, exponential in that case. Okay, so that's the source of harmonic distortion. And so what we do here is, we write now that the input voltage VGS is a sinusoid A naught sine 2 pi f naught t. Plug it here. And what we find is that the small signal drain to source current has a fundamental frequency component, 2 pi f naught here. And along with that, it has a second harmonic here. Now, because the nonlinearity is quadratic, all I get is a second harmonic distortion. I don't get higher order terms like in bipolar transistor. In bipolar transistor, we got the third harmonic and the fourth harmonic and all that. Here, we just get a second harmonic here. So we can find out now, this is the component that I want, and this is the unwanted component that I get. And DC, of course, we can easily filter out using a capacitor here, so we won't bother with it. So second harmonic distortion then, HD2 in percentage would be this term here divided by this particular term, and simplify it and express it in a percentage. So it comes out to be A naught by 4 VGSQ minus VT. So that's a simple expression for harmonic distortion. What is A naught? A naught is the magnitude of the input sinusoid. Okay. So V in is A naught sine 2 pi f naught t, and HD2% is A naught by 4. A naught by 4, yeah, A naught by 4 VGSQ minus VT into 100 here. And note that A naught is nothing but the input voltage here, sinusoidal input voltage here. So we put a V in here, keeping in mind that we are talking about the amplitude only here. We are not talking about the whole sinusoid here. We are talking only about the amplitude here. So instead of A naught, we are writing V in. So V in VGSQ minus VT is nothing but VD sat, and 100 divided by 4 is 25 here. So that's the expression for harmonic distortion in MOSFET amplifier, common source amplifier. The next thing is rearranging. We write V in equal to HD2 by 25 into VD sat, and we know that V naught is equal to AV times V in, and therefore, so for a particular harmonic distortion, what this expression is telling you, that if you have a limit on HD2, say 5% or 10%, then it puts a limit on V in, how large an input voltage you can apply, and therefore it puts a limit on how large an output voltage you can get, because V0 is directly related to V in through this relationship AV times V in. So that's how a limit on output swing is coming from the point of view of distortion, right? So once again, distortion limits the amount of input voltage that you can apply, and output and input are directly related together, so that puts a limit on how large an output voltage you can get here. So this is what we get. V naught is AV, V in, GM. So AV we know is GM RD parallel RL. Now I put a load resistance also, just for the sake of completeness here, V in, and GM, we know this particular term, so a little bit of algebra here, and we get this particular expression there. We get a expression for swing which is limited by distortion here. So all that we have done is taken this GM here, put it here, and V in, instead of V in here, we have taken HD2 by 25 into VD sat and simplified, and we get this expression here. An expression for how much swing can you get, limited by the harmonic distortion. So if you are limited by 5% harmonic distortion, you put 5% here, and whatever is the bias current and RD parallel RL, that will decide the maximum swing that you can get. Okay. So back again then. So yes.
IDP was also a significant DC component.
Which one?
Small signal current. We had a significant DC component which was as strong as the second harmonic. That's going to shift the bias point to.
Yes, it's going to shift a little bit. We saw earlier, remember, in the common collector amplifier, we had seen that as the signal gets distorted, the bias point was shifting. So this is a first order approximation. We ignore it in this case. Okay. So we have an expression for IDSQ RD parallel RL HD2 divided by 12.5 here. Okay. So we have another expression for swing now. This is swing determined by distortion here. Now let me remind you, if you look at this expression, we had derived we had an expression here, VDD Okay, so if you recall, if you go back here, we had for swing, we had this expression, VDD minus VDSQ, which was coming from the positive side here. And we had one coming from the fact that transistor should not enter into linear region here. If you look at this particular one, that's what I'm doing here. If you look at the first term here, the swing that comes from the positive side here, which was VDD minus VDSQ. VDSQ is nothing, so VDD minus VDSQ, in fact, this is not right. VDD is here and VDSQ is here. So VDD minus VDSQ will be simply equal to IDSQ times RD. Now, if you look at this one, IDSQ RD, so V0 max 1 is IDSQ RD here. And V0 max 3 is IDSQ RD parallel RL HD2 by 12.5. And you can clearly see by comparing these two that V0 max 3 will always be less than V0 max 1. Okay, because you have RD parallel RL here. So this RD parallel RL will always be less than RD. And under most cases, we want HD2 which is much smaller than 12.5. And therefore, this term is also less than 1. And therefore, this term will always be lesser than this particular one. Okay, so which means that we have really two limits on voltage swing. One limit is this one, determined by harmonic distortion, and the other one is coming from the fact that you don't want your transistor to enter into linear region. These are the two limits on swing. This one is, as I said, as you can see here, this one is smaller than or larger than this particular one. Okay. Now coming back to this one, this particular limitation on swing. Let me show you something that we had derived for bipolar. For bipolar, note that the swing determined by harmonic distortion was here. ICQ, RC parallel RL, HD2% by 25. Go back and see this swing here. ICQ, same IDSQ. RC parallel RL, RD parallel RL, HD2 by 25, HD2 by 12.5. Why is this difference? 12.5 versus 25? One is an exponential and the other one is quadratic. So note that the effect of harmonic distortion is smaller here, because note that this is 12.5 here and this is 25 here. So distortion is much larger here and it limits the swing more. V0 is, this term is getting divided by 25, while here is getting divided by 12.5. And the differences are coming primarily because a quadratic dependence of drain to source current and voltage here as compared to a exponential dependence of collector current on base emitter voltage. Okay, so that's where the differences are. So it's the same expression. Instead of 25, you have 12.5. You have half there. All right, so coming back to our example, we have VDSQ is equal to 1.3, VSAT equal to here. So we can determine all the limits here. So one limit coming from transistor not entering into triode region is VDSQ minus VSAT is 0.8. The other limit coming from distortion, IDSQ, RD parallel RL, HD2 by 12.5 also comes out to be 0.8 if I take harmonic distortion as 5%. Okay, if you want harmonic distortion to be 10%, then this will come out to be 1.6 volt, and then again the swing will be limited by this particular term. Okay, so here let me just show you. So we have this one here. You can run simulations in microcap, and you can verify that the swing indeed will come out to be 0.8 volt with harmonic distortion close to 5% here. So these are the distortion terms here. So with 0.8 volt swing, one is getting distortion less than 5% here. All right, so that's the output voltage swing here. The important question also arises as to how do I bias my transistor to obtain the maximum swing? Okay, so here in this case, we had already given you a design and we were asking you what is the maximum swing that you will get. So all you need to do is plug in all the values, find out all the limits here, find out whichever one is smaller, and that's the output voltage swing here. But if you're given a design question as to how do you design it so that you get bias maximum voltage swing, and then one proceeds as follows. Again, we have two limits on swing, one from distortion here, the other one from triode region limitation here. And if we look at these two terms, we note that if you're designing for maximum swing, you would like to maximize this term here. and RL is fixed for you. HD2 is also fixed by an application. So these terms are fixed. So the way you would increase V0 is either you would increase IDSQ or you would increase RD or both, right? So what you would do is you would try to increase IDSQ and RD in order to increase this particular one. So yes, this particular voltage, this particular term will go up, but note that IDSQ times RD as you increase, the drop here increases, and therefore VDSQ drops. And as VDSQ drops, this particular term goes down. So as you try to improve this particular term goes down. Or as you try to improve this particular term, this one goes down. So the optimum case is when these two limits are the same. So what you do is optimum drain to source bias, you equate these two. So you equate them together. The rest is now algebra, simplify, and you get the optimum bias point here. VDSQ is equal to VDD, HD2 plus VSAT here, and that's the maximum swing that you can get here. This parameter is 12.51 plus RD by R. Okay, so that's how you bias your transistor to obtain maximum voltage swing for a given harmonic distortion, second harmonic distortion. So the expression looks a little bit complicated here. If you want to remember, you can go ahead and remember. If you don't want to remember, all you need to do is remember these two are the critical terms here. So all you need to do is equate them and rearrange the terms here, and you'll get these terms here. Okay, so that's the maximum swing that you can get given a particular supply voltage. Okay, and this is how you bias. You bias it at VDSQ, which is given over. Okay. All right, let's go back and look at voltage gain in a little bit more detail here. Okay, so voltage gain we said is AV equal to minus GMRD. All right. Now I showed you a particular case of RD was 80K. It was biased at 1.2 volt, and supply voltage was 3.3, and we got a voltage gain of minus 8, and which is very low for most applications. So we are interested in increasing the value of gain. So let's look at this term here and see how can I increase the gain. Okay, that was one kind of a design that I'd given you, not the best of design. So let's look at how one can increase gain in a MOSFET amplifier. So AV equal to minus GMRD, and so we have two terms by which we can increase gain. GM is one, the other one is RD. GM, let's look at GM here. GM is square root 2 IDSQ times beta. Okay, and RD that you see here is nothing but VDD is the supply voltage here, VDSQ is the voltage here. So RD you can write as VDD minus VDSQ by IDSQ. Okay, so we take GM, we take RD, we plug it here, and we get this expression. Okay, AV equal to square root 2 beta by IDSQ, VDD minus VDSQ. All right, so how can we increase the gain now? What are the ways of increasing gain? How do we do it? One is obvious. What do? Decrease the drain to source current. I decrease the drain to source current here, and AV will go up. Okay, what is the other way? By the way, how do I decrease IDSQ? I just decrease the bias voltage. If I decrease the bias voltage, I have less gate to source voltage here, the current will drop. Okay, so that's one way in which we can increase the gain. Yes?
IDSQ will VDD minus VDSQ will go down. And since IDSQ is fixed by 1 by 2 and VDD minus VDSQ is fixed as 1, overall effect would be decreasing AV.
Decreasing what?
If I decrease IDSQ, even VDD minus VDSQ will go down.
Note that RD is like this. If I reduce IDSQ, I'm going to increase RD. That's how I've written. So we are looking at this particular expression here. So we said RD will be equal to VDD minus VDSQ by IDSQ here. Okay, so RD will change. So as I decrease my IDSQ by changing the bias, I'm going to change my RD as well. Okay, so one way that you see here is decreasing IDSQ. What is the other way? Is there another way of increasing the gain? Which one? Beta. That's the other important thing. Yeah. See, unlike bipolar transistor, where we could not change the size of the bipolar transistor. The size did not come into issue at all. While here, if you look at beta, beta is what? Kp, which is a constant. You as a circuit designer, you can't do anything with Kp, but it is Kp multiplied by W by L. And the size of the MOSFET is a design parameter. W by L is under your control. You can decide W by L to be 10 by 1, 50 by 1, 100 by 1, 200 by 1. It's under your control. So that's the other freedom that you have in a MOSFET design. One is, of course, IDSQ. The other one is beta. Okay. Now, let's go forward here. So we know that AV is given by this expression here. But we know that VDSQ, is impacted or has an impact on voltage swing here. So we know that voltage swing, there are two limitations on voltage swing. One is here and the other one is over here. And so what we have done is, suppose you have a certain voltage swing in mind. You want to design your amplifier with a certain voltage swing. So you have to ensure that this particular condition is satisfied, which means that VDSQ has to be larger than V0 minus Vsat, right? If you have a certain voltage swing which is fixed, the application demands a certain voltage swing. This particular expression is telling you VDSQ must be greater than V0 minus Vsat. So what we have done is, we have taken VDSQ and we have said VDSQ must be greater than V0M minus Vsat. This is Vsat. Another way of writing VDSat is 2 IDSQ by beta. And therefore, my gain must be less than or equal to this one, because VDSQ must be greater than this term. And therefore, I can write AV must be less than or equal to this one. Okay. So I've factored in the voltage swing also into my expression. Okay. All right. So this is telling you, of course, this expression is pointing out that if you try to design amplifiers with large voltage swing, V0M large, your gain will get compromised, because V0M subtracts from VDD here, so you lose gain. Large swing will result in smaller voltage gain here. Okay, so it's explicitly showing you the relationship here. All right, let's come back to the gain here. So I've shown you now two ways of increasing the gain here. So in one way, what we have done is we have fixed the size. As I said, L is fixed at 1. We have fixed the size of W at 2. So it's fixed here. Swing I'm taking as a very low value of swing of 0.1. Why am I taking very low? I'm going to use this amplifier at the input stage here, where swing is not that important. Okay, so I've used a swing of 0.1, and note now what I'm doing is I'm steadily reducing IDSQ, starting from 100 microamperes, going to 50, 25, 10, 5, 2, 1, steadily reducing IDSQ. And as I reduce IDSQ, note that if you go back, I'm increasing RD. Okay, I'm increasing RD here, increasingly RD here, and of course, how do I reduce the value of IDSQ? I reduce it by reducing the value of VGS. So I'm reducing VGS, and note what is happening to the gain. Starts 4.4, 7, 10, 18, 26, 43, 62. Okay, so gain is increasing with reduction in current here. With reduction in current, the gain is increasing, and now note what has happened. VGS is become 1.1. And what does 1.1 tell you? Threshold voltage is 1 volt. It has come very close to threshold voltage here. Now, this may give you an impression that my gain will the gain keep on increasing if I keep on reducing IDS? And the answer is no. In fact, the gain is going to saturate very close to this particular value. Once you go into come very close to threshold or go into subthreshold, this expression is no longer valid. This expression is only above threshold. Okay, and once you enter into subthreshold region, this is no longer valid, and one can show that the gain will saturate at a value which is very close to this. So if you keep on decreasing current, eventually the transistor will enter into subthreshold and the gain will saturate. Okay, so that's one way of decreasing the of increasing the gain here. Look at the other way. In this case, we bias the transistor at a fixed current, 25 microamperes. Swing is again 0.1 volt. I even kept RD fixed at 108K. And all we are doing now is increasing W. L is fixed, 1 micron. And what we are doing is steadily increasing W from 2 micron, 5, 10, 20, 50, 100. Note what is happening to the gain. Gain is increasing. Here also, note what is happening is, if current is constant and you increase the size, then you will have to decrease the gate to source voltage. because for a constant current, if you increase the size, if you don't change the gate to source voltage, the current would increase. Okay, and since you want to maintain the current, if you increase the size here, you will have to decrease the gate to source voltage here. So again, note that what is happening is your transistor is increasingly going into subthreshold region, and here also gain will eventually saturate. Okay, so what you are seeing from here is that if I have this particular amplifier, either I require very low current. Note here, current is becoming very low, and therefore my RD is becoming very large, 3 mega ohm, to get a gain of 60 or 70 or whatever it is, a reasonable value here. So that's one way of getting a reasonable value of gain. The other one is I have to use very large size of the transistor to get a reasonable value of gain. Now both of these are problematic. This is problematic. Why? Because making large resistors is difficult. If I'm making a circuit like this on a breadboard or on a PCB, well, a mega ohm resistor is very easy, and you can easily put and make this particular amplifier. But if you're making it on an IC, making large resistors on an IC is difficult, and therefore this is problematic. You can't, easily make a 3 mega ohm or a 10 mega ohm resistor on an IC here because the size of the resistor becomes large. Okay, so that's something that you would like to avoid here. All right, so this is a problem with this particular stage right now is to require high gain. We want very low currents, and along with low currents, you want a large value of RD. And that's the problem here. In this case, what is happening is the size is becoming very, very large. Size is becoming 100 by 1. And there are other disadvantages of size, as you know, that if the size becomes large, all the capacitances will become large, and that will compromise your bandwidth, which we will see in a minute. Okay. So this, is telling you here is that getting large values of gain is difficult from this particular stage with a common source amplifier with a resistive load. And therefore, if you want higher gain without requiring large value of resistor, what is the way to do it? What do we do? I don't want to use a very large value of resistor here because it's difficult to make. So I should replace RD by. We have seen that in bipolar also. How do you get large gain without requiring large supply voltage or large values of RD? Replace the resistor by a transistor. And replace the resistor by a transistor, and the idea is that you get an active load. And what kind of a transistor will we use? Will we use an NMOS or a PMOS? Huh? So we'll see that what you would require is a PMOS transistor here. So if you replace this RD by a PMOS transistor here, then we'll see that you can get large values of gain without requiring large values of resistance. Okay. All right. So the next one is frequency response. So all this, all these discussions are very similar to what we have done. So here is the lower cutoff frequency. Here is the upper cutoff frequency. We know lower cutoff frequency is caused by external capacitances. If you don't have any external capacitances, then you will get a flat curve here. There would be no lower cutoff frequency here. This one, of course, is all caused by internal transistor capacitances. And this, of course, is the mid-frequency region here. I'm not going to do this. The calculations are very similar to bipolar amplifier. Let me look at this particular one, the high frequency one. Okay. So as usual, what you do is replace the transistor by its high frequency model. So you get this expression, you get this equivalent circuit here. For the sake of completeness, I've added an RS also here. So assuming that the source has a resistance as well, and source may have a capacitance also. So we have put a CS also to make it more general. We have CGS, CGD, we have drain to body, and at the load, for example, in addition, you can have a load capacitor also. The load, for example, this amplifier could be driving another common source stage. So if it's driving another common source stage, so there would be an output capacitance as well. Okay. All right, so we have put CL. If you want, you can put an RL also and make it more general. So once you have a circuit like this, how do you determine the upper cutoff frequency? What is the general method? What do we do? Well, the most accurate and general method is what you do is the transfer function, right? So you write down the transfer function, and so it will take you some time. Replace all the capacitors, and you would write it down. You have all these terms here. Okay. Note that in all these single stage amplifiers, what you end up getting is the denominator is a second order polynomial. So you get 2 poles, and in the numerator you get a 0. So in almost all of them, you'll get 2 poles and a 0. Okay. Now from here, we know that if you assume a dominant pole, so you have P1 and P2. If you assume a dominant pole, let's say P1 is much smaller than P2, then you can determine P1 by simply looking at the prefactor of the first order term. And so P1 will be simply equal to 1 by G. And once you know P1 and P2 equal to 1 by H, so you can get both the poles. All right. So that's how you end up getting the first pole and the second pole. And many times you make an approximation that you have a dominant pole, as I said. Dominant pole is P1, and so 3 dB frequency is nothing but the dominant pole. Okay. Most of the time, the analysis is fine. Okay. And you can check that the other pole is much farther away as compared to the first pole here. So that's a more general way of doing frequency response. The other way, as all of you know, that we have been doing open circuit time constant approach. Due to each capacitor, determine a time constant, sum them up, and that gives you a 3 dB frequency. And in that context, we use Miller's theorem. Anytime you have a capacitance between input and output port here, what you do is you bring the capacitor, one to the input side, the other to the output side. All of you know this, 1 minus AV here, 1 minus 1 by AV here. And this is what we'll do here. So we'll take CGD here, and we'll take CGD, we'll bring CGD here, 1 minus AV, and another part of CGD goes 1 minus 1 by AV here. And we have the drain to body capacitance as usual here, CGS is here. Okay. And RS of course is here. So now things simplify. The two capacitors now are in parallel, so you simply add them up. This one are also in parallel, you simply add them up. So you have two capacitors here, one capacitance of the input side here, CGS plus CGD 1 minus AV, and the time constant due to this is straightforward. This capacitor sees a resistor of RS, so time constant is straightforward here. This capacitor, the sum, sees nothing but RD parallel R0, and that also is, and RD parallel R0 is only RD, so the time constant, this should be T out, so that's RD into C out. And as all of you know, in Miller's theorem, the major problem is what is the value of AV, and we have said that use a value of AV, which is the low frequency value, right? Low frequency value, which is simply equal to GM times RD. All right, low frequency or mid frequency value. So that's what we do. And so that's then the frequency response then is straightforward. It's calculated in the same manner that we have been doing, finding out the time constants and the two time constants, one from the input side, one from the output side, simply sum them up and you have the value of 3 dB frequency. Except that you have to do a little bit of a calculation in finding all the capacitors. Okay? All the capacitor values have to be found. And capacitor values are a little bit involved, as you can see here. CGS is 2/3. Well, you have to remember the expression. There are no shortcuts here. But expressions are easy to remember. All that you know is this is nothing but a PN junction capacitance. That's what the expression is. And there are two terms to it. One is an area term, the other one is perimeter term. So this is the source to body. This is not bottom or side wall. This is net capacitance source to body, net capacitance drain to body. And as I said, all these values will be given to you, Cox prime, CGS0, PB and all that. All the parameters are given. And all you need to do is substitute the source to body voltage here, drain to body voltage here. And you have to know the area and the perimeter. And how do you know area and the perimeter? Well, the values are given to you here, expressions. AS is W into LS, 2LS plus W and all that is given to you. What you don't have in a schematic is the value of LS and LD. And as I said, as a first order approximation, you can simply say LS equal to L. Okay, as a first order approximation. These values LS and LD become available only after you do the layout. Once you do the layout, then you have the whole area available to you, and then you know what is LS and what is LD here. But as a first order approximation, you can assume LS is basically equal to L, and therefore you have PS and AS and PD and all that you have. Plug it into all these terms, and you have all the capacitors, like I did here. So we have CGS equal to 4 femtofarad, CGD 0.4, and drain to body 4. And then we go ahead, we plug in all the values here. In this case, I don't have any RS, so my first term actually disappears. I have only second term RD here. I get 0.45 gigahertz 3 dB. My simulation also shows 0.44 gigahertz. So these expressions work reasonably well. Okay. All right. So that sort of finishes with the frequency response, and that's a summary of our common source amplifier. We have a common source amplifier here, bias at 25 microamperes, gain is -8, output resistance is 80K, swing 0.8 volt, 3 dB, 0.45 gigahertz. So this is where we are, and the next thing is, how do we improve this amplifier? All right, you can see the problems with this amplifier. One is the gain. Gain is low. The swing is also low because you have 3.3 volt here. The swing is only 0.8 here. And frequency response looks pretty good, 0.45 gigahertz, only because we have not put a source resistance here. In fact, suppose you have an amplifier like this. This is more realistic. You have one common source amplifier, which is driving another common source amplifier. So normally you're going to make multi-stage amplifiers. So if I want to calculate frequency response here, how do I do it? For this amplifier. If I want to calculate the gain of this amplifier, how do I do it? Very simple. I calculate the gain of the first stage. I calculate the gain of the second stage, simply multiply it together. Note the simplicity because there is no loading effect of the second stage here. I don't have to put Rn of the second stage in parallel with this. So it's simply the gain of the first stage, open circuit gain of the first stage, AV1, multiplied by open circuit gain of the second stage, AV2, multiply them together, you have the overall gain. So gain is very easy. What is the net input resistance? Looking from here, obviously infinite. What is the net output resistance? Net output resistance of the amplifier? Well, net output resistance is looking from here. What will you get? Basically 80K. So you know the input resistance is infinite. Output resistance is 80K. Voltage gain you can easily find out. Swing will be determined by this particular stage here. So using the expressions that we have, swing also you can determine. How do you find the frequency response? Frequency response will not be determined by the second stage or the first stage. How do you determine that? Well, our approach is open circuit time constant approach, which means that for each capacitor, find out the resistance that it sees and sum up the time constant. So what you do is, you do the following here. This is our approach. So you say time constants are here. So you identify 3 nodes that are there in the circuit. You see, capacitors exist at a particular node. So I have 3 nodes here. 1, 2, and 3 here. The other node that you may think that I have a node here. Yes, it is a node here, but this node is at a constant voltage. It doesn't matter. This particular node is ground, obviously doesn't matter. So I have 3 nodes here, and all I need to do is find out what is the net resistance at this node, what is the net capacitance at this node. Why am I writing R1 equal to 0? Net resistance at this particular node. What do I mean by net resistance at a node? It means the resistance between this node and ground. Okay? So why is the net resistance 0? Well, if you are at this node, if you look right, what do you see? At this node, if you look right, you see infinite. If you look left, 0. And 0 comes in parallel with infinite, so the net resistance is 0. Okay? What is the net capacitance at this node? Can everybody see now net capacitance at this node? One is CGS, which is here. The other one is between these 2 nodes, I have CGD, but that gets multiplied by the Miller's effect, 1 minus AV1. Okay, AV1 is the gain of this one. So that's the net capacitance at this node. All right. If I had a source resistance, you would have put here R1 equal to Rs. The net resistance at this node, everybody sees, is 72K. Resistance looking right, infinite. Resistance looking left is 72K in parallel with R0. R0 we neglect, so it's 72K. The net capacitance at this node, it will come from M1 and it will come from M2. From M2, it will be CGS2, that's the first term, and CGD2 multiplied by Miller's effect. So that's all the capacitors that come from the M2. From M1, there's a capacitance at this node which is drain to body capacitance here, CDB1, and there is a capacitance between gate to drain, and we apply Miller's effect again, which is 1 minus 1 by AB1. So that's the net capacitor at this particular node. So you multiply them together, you get this second time constant. And then you look at this one, net resistance is 80K, and the net capacitance at this node is drain to body and gate to drain of the 2 multiplied again by 1 minus 1 by AV2, which is the Miller's effect. So all you do is you multiply these two together, multiply these two together, multiply these two together, sum them up, and you get the value of 3 dB frequency. So any amplifier that you're given, all you need to do is identify all the nodes in the circuit. At each node, find out the net resistance, the net capacitance in the manner that I've shown you, and just sum them up and you get the 3 dB. That's all that is required for any amplifier here. All right, so let's stop here.